We're now moving on to Chapter 16. It's a continuation of equilibrium, but we're going to be talking about acids and bases. You'll be learning a little more, and you'll learn about equilibrium reactions for acids and bases. First, we're going to start with a few definitions. And you've seen acids and bases before, so some of this will be review. So an Arrhenius acid is an acid that produces H+ in solution. An Arrhenius base is something that produces hydroxide ion in solution. Then we have a Bronsted-Lowry acid and a Bronsted-Lowry base. Acids are proton, and H+ is just a proton because an H has one proton, one electron, so H+ is just the proton because you've lost the electron. So a Bronsted-Lowry acid donates protons. Bases accept protons. So here's an acid. Here's a base. The base is going to accept this H+ from the acid, and the acid is going to donate this H+ to the base. And we get H3O+ because the HCl donated the proton to the water. And Cl- is left over because HCl donated its proton. So here we accepted the proton. Did I say donate? The base accepts the proton to become H3O+. The acid donates the proton to become Cl-. Now, conjugate acid-base pairs. It's an acid-base pair that differs by a proton. So we can look and see this HA, this would be a generic acid, looks very similar to this A-. The bases are written in blue here and the acid's in pink. So this right here would be a conjugate with this. This would be a conjugate acid-base pair, the A- and the HA. The A- is the conjugate base of the HA because these are different just by a proton. And water and hydronium ion, H3O+, right here, it's called hydronium. This is a conjugate acid-base pair. Here's my base. It accepts a proton, so it becomes an acid, but it was a base because it's the proton acceptor. And this is just showing you how this little proton is going to go from here over to the water, and that's how we get the hydronium. And this piece, this big purple A- is left all by itself because the H+ was given away. All right, so here are a couple of problems, and the answers are just below them. You want to identify the acid and the base and the conjugate acid and conjugate base. So you look for something that's similar. HCl, you can pause this if you want to do it on your own. HCl looks like Cl-, so there's a pair. Now the acid has an extra H compared to the base. So here's my acid and my conjugate base. All right, I'm going to show, so pause for a minute. I'm just going to show you the answers to these. There we go. I didn't go over the other example. Hopefully you could figure that out. So HCN, Cn-, there's a pair right there. This is the acid of the pair and the base of the pair because the acid has an extra proton or extra H+. Okay, two more problems. Go ahead and pause. And I'm about to show you the answers. We learned this before, so this should be review. Okay. Next concept, the pH scale. There's a lot of information here. Okay, pH scale lets you know how acidic or basic a solution is. The lower the pH, the more acidic. The higher the pH, the more basic. pH 7 is neutral. So 1 through 6, acid. 8 through 14, base. And these equations, you do not have to memorize them, but you will need to know how to use them. We do not use the ln key, we use the log key on the calculator. There's a little 10 to the x on your calculator, and then the alternate function is the log function. So we use these 7 equations, and we'll do some problems here. One important thing about these is that H+ and hydronium ion are used interchangeably. So wherever you see H+, that is also the same as the hydronium ion concentration because H+ will not just sit in water, it will always attach itself onto a water molecule to instantaneously, spontaneously, however you want to say it, form hydronium ion. This reaction goes to completion. Going to completion, going all the way to the right. Okay, so we're going to use these 6 equations up here to solve each of these problems. Okay, let's just focus on the left for now. So don't, oops, what did I do? Ah, oh dear. Okay, there we go. Don't look at the solutions on the right as we're going through this. So HI, we look up here, when we notice this is a strong acid, that means it dissociates completely into H plus and I minus. So there's one H plus for each HI because it dissociates completely. So the H plus is just the HI concentration. That part's easy. Oops. Well, that's the bottom down there. The H plus is just 0.1 molar. I did this one a little bit backwards. Now for the pH, we have this equation. pH is negative log of H plus. And we see that H plus is 0.1 because this splits completely. We have 1 H, so there's 0.1 molar H plus. So pH is negative log of 0.1, which is 1. What did I do next? pOH. Oh, if you have the pH, it's easy. pH and pOH always add up to 14. So if pH is 1, the pOH has to be 13, right here. Ignore the right side. We'll go over that in a minute. And then we already said H plus was 0.1. So now, to get the OH, I could either use this equation, 0.1 times the OH is 10 to the negative 14, or I also have pOH is 13, which means OH, I can use this equation right here. OH is 10 to the negative pOH, which would be 10 to the negative 13. There you go. Okay, so each of these problems is kind of like a puzzle. You have to figure out which equation should I use and how do I solve it. So you can pause this, do whatever you want. I'm going to go through this one. I've given you the pH already, and I've asked you to find all these different things. Well, if I have pH, it's really easy to find H plus, because H plus is just 10 to the negative pH. So that would be 10 to the negative 2.5. You'd have to plug that into your calculator. You'll get a concentration. Also, pH and pOH, I know they add up to 14. So if I plug in 2.5 here, I can solve for the pOH. And again, pause if you want to do this on your own. Obviously the pH is 2.5, it was given. There we go. We just add pH and pOH is 14, so we get the pOH. So the pOH is 11.5. Okay, and then H plus is just 10 to the negative pH. Plug that in your calculator. And OH minus is 10 to the negative pOH. It's one of our equations. You just look at your equations. pOH is negative log of OH. OH is 10 to the negative pOH. So 10 to a power and log, the logarithm function, those are inverse functions. Okay, last one. This is a little trickier because I have 2 OHs for every one BaOH2. This is fully soluble. It's a soluble ionic compound. So if I have 0.15 molar barium hydroxide and there's 2 OHs in one of these, hopefully you recognize the OH concentration will be double this because for every one of these I have 2 OHs. So OH is going to be 0.30. The rest is easy. How do you get pOH? That's right. And you can pause again if you want to do this on your own. pOH is negative log of OH minus. You put this in your calculator, take the log, change the sign, and you get pOH is 0.52. Now pH and pOH has to be equal 14, so it's easy. You get the pH from this equation right here. And then H plus, we know H plus is 10 to the negative pH. That's this equation. Where is that equation? H plus, 10 to the negative pH. So I just do 10 to the negative 13.5, plug that 13.5 in here, and I get this answer. Okay. And would these be acidic, basic, or neutral? You just look at your pH. pH 1, the answer is below. I'm not going to tell you. pH 2.5, pH, where did it go? 13.5. So remember, 7's the cutoff. Here's your answers. Oops. There you go. All right, next section, acid strength. Oh, notice we skipped 16 too. It was just about water. We're not going to worry about water because we use water with the pH scale and we're seeing water all over. We're not going to talk about water. Okay, acid strength. Remember we have our 7 strong acids. There's another one, but we're not going to worry about that one. So we have our 7 strong acids. You should memorize those. And all other acids are weak. All acids have an equilibrium constant Ka, but weak ones have a small equilibrium constant. These would have a large equilibrium constant because the reaction of these breaking apart would go to completion. Weak acids, the reaction does not go to completion. Okay, so for this reaction where HA is any acid, this is a generic form for an acid. A minus is the generic form of the conjugate base for our generic acid. And the Ka, remember, is products over reactants. I'm sorry, I did not write in. These are aqueous. Okay, fixed that. We need to move this over a little bit. So here's my reaction right here. And I only include the aqueous substances in the reaction. So I have products, the aqueous products over the aqueous reactant, and I leave water out. So that would be my Ka for any acid reaction. Also, notice I call this an acid dissociation constant. Dissociate or ionize. Dissociate is to break apart. Ionize is to cause ions to be created. Sometimes these are called acid ionization constants or acid dissociation constants. You have to know both of those terms. All right, and here are some Ka values. We will be using these. Notice here are 2 strong acids. Actually, all 3 of these are strong acids. And they let you know this one, actually, they give you a Ka, it's approximately 20, which means there's 20 times as much NO3 minus as HNO3. And these 2 are larger than 20. Okay, and as we go down this particular group, the Ka gets smaller and smaller and smaller. Okay, so the larger the Ka, the stronger the acid. That's because when K gets big, that means we have more products. Remember, K is products over reactants. So if we have a lot of products, K is really big, that means we have a lot of H3O+. We have a lot of the conjugate base, but those are, they don't add much to the pH compared to a hydronium ion. That's our measure of how basic something is. This is the same as our H+. So the bigger the Ka, the more the products we have, the more H+ we have, the stronger the acid. So larger Ka, stronger the acid. Now, we've talked about acids and conjugate bases. As our acid strength goes up, the conjugate base of that acid, its strength goes down. So there's an inverse relationship between conjugate acid-base pairs. And strong acids have extremely weak conjugate bases. They're weaker than water. And the stronger the acid, that means the larger the Ka, the farther to the right, or the more to completion the reaction goes, and the weaker the conjugate base. We just said that right here, that as acid strength goes up, conjugate base strength decreases. Notice I've said that twice. That's important. Okay, so stronger acids, equilibrium lies farther to the right. Weaker acids, equilibrium lies further to the left. Not all the way to the left. It depends on the K, of course. If you have a really small K, equilibrium lies almost all the way to the left. Large K, almost all the way to the right. All right, so you want to fill these in. If equilibrium lies to the right, the value of K is it large or small? And if equilibrium lies to the left, the value for Ka is large or small. I'm going to write these in, and there are your answers. Okay. Okay. We're going to use the chart, and we're going to rank the acid strength. Now, we're going to have to look up HCN and HSO4 minus. So we look those up. Here we go, right here. HCN, let's see, and again, you can do these on your own. So the HCN, the Ka is on the order of 10 to the minus 16. HSO4, 10 to the minus 2. Which of these is bigger? The HSO4. So which one is stronger? The HSO4. Okay, so the answer for this one is HSO4 minus. Sorry, not just HSO4. If you want to do these on your own, you can, but I will go through those with you. So go ahead and pause. Hydrofluoric acid, HF, or acetic acid? Let's see, hydrofluoric acid. Where is it? There it is, right there. And acetic acid, right there. Hydrofluoric acid has a larger Ka, so it is a stronger acid. Notice its conjugate would be weaker than acetic acid's conjugate, but that's not what the question asked. Just remember, the stronger the acid, the weaker the conjugate base. So HF is stronger than acetic acid. Okay, now ranking these, we're going to look up all of these different Kas, and the larger the Ka, the stronger the acid. So this should be very straightforward. I'm going to pause and just put up the solution. And there you have it. Okay. Hopefully I did that right. I'm pretty sure I did. Okay, now I've mentioned this a few times. Conjugate bases. They have an ionization constant also called a Kb, B for base, A for acid. If you ever see Ka, we're talking about the acid. With B, we're talking about a base. If you see a C down here, that's a concentration. If you see nothing, it's just concentration. If you see a P down here, that means you're using pressures. Okay, as Ka goes up for an acid, we said the base gets weaker, which means Kb is smaller for the conjugate base. The stronger the acid, the weaker its conjugate base. I know you've now heard that about 5 times. Obviously, that's an important concept. All right, if Kb is less than 1, then A minus is a weak base. When I say A minus, I'm talking about this A minus, that generic weak base right there. This would be a base that's an ion as opposed to a molecular base. Okay, so if Kb, the base constant, is less than 1, A minus is a weak base. So we're going to range these from weakest to strongest as bases. Rank these bases. So I've only given you Kas. You need to look up the Kas for all of this, and the bigger the Ka, the weaker the base. So the smaller the Ka, the stronger the base. We're going to rank these from weakest to strongest. I'm going to pause and put up the answer. You take some time, look at your Kas in that chart, and see if you can figure it out. I gave you a little hint here. Oops. Okay. So pause. I'm about to show the answer with a big explanation. Okay. So sulfate is the weakest base because its conjugate acid has the largest Ka. HCN had the smallest Ka, so Cn minus is the strongest weak base. And then acetate, the conjugate of acetic acid, is right in the middle. All right, last thing. Section 16.5, weak acids and acid ionization constants. We've talked about these acid ionization. I also called it a dissociation constant. You'll see both those words interchangeably. So you've got to get used to them. We're going to do some calculating problems, equilibrium problems. Iceboxes. Okay, you already learned about iceboxes. Find the pH of a 0.75 molar aqueous solution of HCN. That means we have only HCN present, and we're going to find out at equilibrium what are the concentrations of the other things. We need a reaction. Well, whenever we have an acid, you should recognize this is an acid and I have a Ka. You do the acid plus water, and you predict what the products would be. So acid plus water will make my conjugate base and hydronium ion. So I need my initial would be 0.75 for the HCN. Water I don't worry about, it's a liquid. These 3 things are aqueous. This would be 0 and 0 because I'm not starting out with any of that present. And then reaction must go to the right. Reaction has to go to the right because these are 0. So this will go down by x because there's no coefficient here. Up by x, down, up. And then my E row, we just add up the I and the C. Now I can do an equation x squared minus 0.75 minus x equals K. Okay, so I've written my equation right here. X squared, products over reactants, right here, products over reactants equals to Ka. That's my definition for Ka. And I just substituted the Ka in. Now, these problems are ugly if you try to solve that quadratic. We don't want to do that, so we make an assumption. Notice that Ka is really small. This Ka right here is tiny. It's much, much less than 1. When K is really small, X is really small. So X is going to be much less than 1 for sure if our K is so small. So since it's much less than 1, we're going to assume it's much less than 0.75. That's the assumption we're making. And if that is true, then 0.75 minus x is approximately equal to 0.75. This is a big jump. We've never done anything like this before, and you just have to accept it. So now we have x squared over 0.75, because we made the assumption, is 6.2 times 10 to the minus 10. And we solve that for x. Okay, so I solved that for x, and notice this answer for x is definitely much less than 0.75. So we're okay. You always have to check your assumption. Now, the question asked for the pH. And pH I get from H+. I have X, which is my H+ concentration. So to get the pH, this is H+, and pH is negative log of H+. So I just take the log of that number, and I get pH is 4.7. And I'm done. I don't have to go back and fill in anything in my ice box. I don't have to do anything with this over here. I just have to make sure I answered the question that was asked. Calculate the pH. All right, next problem. This one's a bit different. I'm telling you how much has dissociated. So first I have to figure out the reaction. I've got my lactic acid, and I add water to it, and I get the conjugate base and lactate. Okay, so here's my reaction. I fill in the initial column. So these are just 0, because I was told I didn't have any of that. I just have a 0.1 molar lactic acid solution. Now, change. We have to go minus x, x, x. And then this will be 0.1 minus x, x, and x. But I was told that 3.7% dissociated. That means that's 3.7% of the 0.1 molar. My initial concentration is 0.1. So 3.7%. This is not 3.7%. This is 3.7%. So this is 0.0037. Okay. That is how much dissociated. I just fixed the math there. That is how much dissociated, how much actually reacted. That is what this means. So if that much reacted, that's saying that x is 0.0037. Not negative x, x. So x is 0.0037. 0.0037, 0.1 minus 0.0037, which is basically 0.1. It's 0.9963, but, well, we could keep it as 0.996. And we don't have to worry about that assumption piece. And now K, it asks us to calculate K. That's just products over reactants. And I had another little math issue over here that was 0.09963. Some of you probably caught that and were ready to call me, but we've got this fixed. So we find our K, and we only had 2 sig figs, so 1.4 times 10 to the minus 4. All right, very last problem. You can try this one on your own. I'm just going to put up the solution. I've given you the reaction already, but if you want to try to predict that on your own, I hid it for a moment. It would be the HOCl plus the water. Figure out what your products are. Here we go. And you're going to fill out an ice box. You can pause this. I'm going to go ahead and solve the whole thing. You're going to have to make that assumption again about x being small. 0.200. Reaction has to go to the right. Minus x, x, x. 0.2 minus x, x, x. Now I was given my Ka, so I know x squared over 0.2 minus x is equal to my Ka. Definition of Ka, 3.1 times 10 to the minus 8. I'm going to assume, because I have such a small Ka, the reaction doesn't go far to the right. I will assume x is much less than 0.2, which means x squared over 0.2 is 3.1 times 10 to the minus 8th, because this assumption means that 0.2 minus x is approximately 0.2. So if I have that, then I know we're good. So this piece right here is approximately 0.2. All right, and that gives us x Right, that gives us x is 7.9 times 10 to the minus 5. The problem asked us for the pH, which is from the H+. This is the H+. pH is negative log of H+, which is 4.1. Okay, and we will do a bunch of sample problems in class.